Here I am playing a 10-minute recording made by Ruelof PA0RDT. I'm tuned to VJ, a non-directional beacon. The carrier is on 328 kilohertz, or close to that. It's here. And I'm listening to the lower sideband at 327.6, or more precisely .6027. So the carrier of the sideband is here. The dots from the V, DDD, produce a sideband here, and on the other side here. We can see them in the waterfall here and here. The dashes produce sidebands closer to the carrier here in this region. And there are other stations on the frequencies that contribute also. The filter is set to just allow the keying sidebands from the dots. I can make the filter just a little bit narrower to put those sidebands outside. Oh, like that. And it takes a little time because there's a long processing delay here. But it's quite clear we cannot copy anymore. Or only if we know what the signal is. So those sidebands has to be included. Like this. I have set the S-meter calibration here to a value that puts the 0 point on the dBm scale at the level of the signal VJ. It varies, of course, a little bit from time to time. Noise can add, but noise can also subtract from the signal. And the signal itself varies with time due to the variations of propagation. The noise floor here, it's very unstable, of course, because there is no averaging. I can do averaging by running the S-meter slower, like this. Here is the signal, and it is now about 3 dB weaker, 2 or 3 dB weaker. It's because what we see in this peak is the average over the whole keying sequence, this entire region. And it's about 2 decibels below the reference level of 0. And we can see the noise floor. It's here, here, and this is the average noise floor. And it varies, of course, a little from time to time, but I would say 11 decibels, signal to noise ratio. It's possible to degrade the signal by pressing F7. So I do that several times now. Oops. That was unintended, but it doesn't matter. So I press F7. a noise level of 15 bits. And the noise has increased. Up to here. But I think one could say that this can still be copied. Signal to noise level is now 8 decibels. And F7 once more. And I forget, I have to click the mouse to get focus to Linrad. So I get these lines that we don't have to worry about now. And we should have got now F10 to see the mouse. Now the noise floor is 3 dB higher, and it's not possible anymore to copy the signal. And we can see that the noise significantly adds to the signal. It is no longer at this level, it is a little bit higher now and then. So this represents the limit, 15.5 bit. This image was made by Roelof, PA0RDT, who made the recording also. It is made from this 10-minute recording using Linrad to play audio into this NDBfinder. The NDBs repeat in this one at about 8 seconds. It means 75 repetitions. And on the original file we can see very clear VJ, and it decodes VJ automatically. Here the same file is played, but now with 16-bit noise added. That's 3 dB worse than the threshold I just showed for listening on one sideband in real time. But NDBfinder, it can detect, and it comes up with VJ. And here is with 17 bits of noise. It is still detecting VJ. It's a little bit hard to see that, but you can see dit da, di da da da. So it works at this point. And I don't know the mechanisms, but it is the average of 75 repetitions. Here I'm running 2 cascaded instances of Linrad. The first one on the left hand side, it's running in AM mode in Coherent 2. It means that the narrow filter with the curve you can see here at the center, it's very sharp, and the carrier belonging to VJ is centered in that filter. Since there are very few bins on the filter, I have to set the decimation in the time domain and also the filtering. That's 2 in this box. That uses up quite a bit of CPU time. It's 62% in the thread doing that job. The carrier that comes through the filter is used to extract the phase, and the phase is used to do synchronous detection of the A2 that the NDB is using. So it means we get two signals, I and Q, where I is the AM modulation and Q is the phase or frequency modulation, which there should be nothing of. The second instance of Linrad here is receiving I and Q over the network. There are all sorts of error messages because this is a little bit experimental and I don't know if it will be worth the trouble to optimize these things, because I don't know whether there really will be enough interest in it. You can see here it says no input occasionally, because the data from the network comes in big chunks and then there is nothing for a long time. But it doesn't really mean anything. As you can hear, the signal is quite okay. I've set the S meter to show about 0 dBm for the signal Vj, and we can see it very clearly here now. In the baseband, the green dots are the AM components, and the magenta dots are the FM components, and you see the spectrum of Vj with the dot sidebands here and here, just inside the edge of the brick wall filter. Then closer to the carrier we have various components belonging to the dashes and their relative positions. And outside the filter there are other peaks, here and here, but they don't have a fixed phase relation to the carrier of the Vj beacon, because they belong to other NDBs. So they are equally strong in I and Q. Now I can start to degrade the SN ratio here by pressing F7 in the AM. And this was the limit before. I go one step further. This is now 16 bits. This could not be heard when listening to one sideband. And there is a considerable processing delay. It's a real time, but with a delay. We could use from a signal from the antenna rather than from a decoding to listen directly like this. And now it's obvious that the signal to noise ratio has degraded in the loudspeaker. It's no problem to find this signal. Looking at 328, we have several carriers. The strongest one is here. Despite the degradation, it's still about 30 decibels above the noise floor, so it's an easy to find carrier, as you can also see in the waterfall. There are several other carriers, and I could detect what they are sending. Maybe not now, but if I did not add the random noise, it would be easy to copy several more stations using this carrier frequency. They are not exact on the frequency, and that's how we can separate them. So this is what can be obtained by using coherent detection of the A2 signal that is used by the NDBs. I have now applied coherent processing to the second instance of Linrad. And you can see that the carrier of the sideband here is something like, 15 decibels above the noise floor. Now we must remember that the total duty of this signal is very low. The carrier is off for most of the time. It's necessary to not set a too high resolution, because the phase is constant within one sequence, but the next sequence does not have a correlated phase. So the gain we can get from coherent processing is limited. But copying VJ here is fairly easy, and it's at the level of added noise of 16 dB. So I go to the AM, the first instance, and degrade by 3 more decibels, like that. And this will probably not make the decode easy anymore. And the processing delay is large. Here you can see the increased noise floor in the main waterfall, and then we have the delay of the second instance of Linrad. And since there is no averaging, 3 dB is not so easy to see. But here you can see in the waterfall, here the noise floor goes up. And this is very much at the limit. We can still copy, and it's clear from the baseband graph, as you can see here, that the carrier is about 10 dB above the noise floor. So the coherent processing is still working, and it's removing noise that is out of phase with the carrier. We could do averaging on this signal and get a very clear signal pretty fast. But if I go to the level which was the limit for NDBfinder, so I go here and press F7. I didn't mention before, but at 18 dB, NDBfinder fails completely. Stepping out half bits is a new thing in Linrad, and Roelof did not have it when he made his images. So this is a level where NDBfinder could detect the station marginally. And we will see. I will change the waterfall gain. It's now 28. I make it, let's say, 34. And things go very slowly because there are long integration times and very narrow bandwidths. Here is the line where the noise floor was increased again by 3 dB. Oops, and that shouldn't have clicked because that would move the center frequency. So I wait for a while. Look where the signal is. It comes here. It seems I have to wait a little bit. Yes, so I click on it. Could get it back into the center of the passband. Here now it is very hard to copy VJ, or maybe I would say more or less impossible. The resolution of the second instance of Linrod is now much higher. From here to here is 1 Hertz, and the number of FFT bins for 1 Hertz is about 90, which means that the FFT spans about 90 seconds. Each transform has the length. Now they overlap, so they come at about twice that rate. I'm playing the 10-minute recording over and over again, and from here to here is 10 minutes, and then again 10 minutes, and now I'm towards the end of the recording. I'm not using coherent detection, I'm just listening in the second instance of Linrod, just listening in the matched bandwidth. But up here in the coherent graph, as I call it, it's showing I and Q, I horizontally and Q vertically. In the gaps between keying we have this blob, and when the signal is sent you have another blob here. We can see that the RMS diameter of this is in the order of 5 times lower than the distance between the center from here to here. And that is in good agreement with what we can see on the S-meter graph. The signal, which is I only, is at 0, while the noise floor is about 15 decibels below. 15 decibels, that's about 30 times, and that is in power, so in amplitude it means 5.5 times. Now I will switch in the coherent processing by clicking this box. Like this. And this is comfortable copy, but of course this is with no extra noise added. So I go to the first instance of Linrod and press F7 in order to increase the noise to degrade the signal. Now the degradation is 17 bits. That's the level where NDBfinder could detect, but close to its threshold. We can see in the coherent graph here that the noise is now reaching fairly close to where the signal is. The signal amplitude has not changed, so it has its center here, and the noise is here, and we can see that the noise occasionally goes all the way out to the same amplitude as the signal, and in all directions, because it's random noise, so it could be in the opposite phase as compared to the signal, or 90 degrees, plus or minus. Here it is possible to make a big improvement. If you listen, you can perhaps still hear VJ, but one has to listen for quite some time to become convinced that that is really what is repeating. It will be possible to do a significant improvement here, because we can take the average from repetition to repetition, and we can do that with the amplitudes rather than the powers. That means coherent averaging, which means that the signal to noise ratio would improve in proportion to the number of averages. So in 10 minutes there will be 75 averages, and that is, what is it? Not quite 20 decibels, but very much. While the NDBfinder is using incoherent averaging, so improvement is the square root of the number of averages, and the square root of 75 is, well, I don't know, 9, 8.5, something. So it's 9 decibels about. The coherent averaging cannot help to hear a signal that is 20 decibels weaker, because it is required that the carrier is established with good enough accuracy. And we can see here, this carrier is about 25 decibels above the noise. And I would think 10 decibels would be with margin good enough to get an accurate enough phase for the coherent averaging to be for the coherent processing to be successful. Here the signal is at 60 and the noise floor is at 42 something. So that is 18 decibels. It means we could detect a signal easily that is about 8 decibels weaker than this beacon. So that's 8 decibels below the limit of NDBfinder. But that requires coherent averaging, something I have not added into Linrad, and I'm not so sure I will do that. It's a fairly simple thing to add in a separate program for anyone interested. I now press F7 to add 9 decibels more noise. That is 18.5 bits. With 5 averages here, we can now see the carriers reasonably well in the waterfall. If this waterfall would cover the entire screen on a modern screen with 2000 pixels or something, it would show about 22 Hertz, around the 400 Hertz modulation frequency. The waterfall is very slow, but run it for half an hour and then look at the signals that are visible in the waterfall. The one that belongs to the selected carrier would be visible only in the green track, and with coherent averaging over the repetitions, you could detect NDBs far below what you can do in any other way. Here are the processing parameters for the second instance of Linrad. And for the first one, you can see here I have now set a 4 times narrower bandwidth in the second instance of Linrad. That means that each transform in the baseband here spans a time of 360 seconds. That's 6 minutes. Which means that 5 transforms would be 30 seconds, but they overlap by 50%, so it's actually 15 seconds for each line in the waterfall. But this averaged spectrum here, it's the average over half an hour. The file is only 10 minutes, so the noise here is higher than it would actually be. I mean the scattering of between the points here in the noise floor. So the signals would be more visible if this was from an antenna, so it was actually 30 minutes of real signal. Here the carrier, I have not worried to center it. Everything is so slow here. So I just want to show it. We can see it at something like 13 decibels above the noise, and the sideband here is separated by something like 0.13 Hertz. Well, it has to be 0.125 because it's the sideband associated with the repetition rate. The keying sequence repeats every 8 seconds, so it's 1/8 that is the frequency. So we have sidebands on this side and on the other side. The sidebands seem to be a little different in amplitude, which means that there is probably a small amount of frequency modulation also associated with this keying. Hard to say from this graph. The waterfall, is it now 5 lines, means 1 hour and 15 minutes. And here the signals are well visible and the noise degradation is 18.5 bit. It is probably possible to do coherent averaging at the signal level that is 3 or 6 decibels lower than this. Finding the signal would not be difficult, but the time it would take would be very long.